Hi, good afternoon. I hope everybody had a good lunch. And now we're going to talk about C++ and Rust. So hopefully you all have a big pile of C++ out there and you've been looking at options. But why would you want to convert your code to Rust? We have seen a lot of concern around C++ memory safety, and our company pledged to be secure by design. According to CISA, the memory safety vulnerabilities are the most prevalent type of disclosed software vulnerability. So we'd really like to get ahead of that and mitigate that entire class of problems. We also believe that security software, as a general rule, should be held to a higher level of memory safety and correctness guarantees, both of which are supported by Rust, the language. Now, Rust itself has quite a few advantages over C++. There's no undefined behavior in safe Rust. It's got a stronger, more modern type system. And the memory safety guarantees through ownership and borrow checking are very substantial. For a 10,000-foot view of ownership, it's basically the idea that every single value has a single owner, and when that owner gives up the value, it is freed immediately. And that owned value can be borrowed either immutably by as many references as you want, or a single immutable or a mutable reference. So the combination of those factors produces a lot of the memory safety guarantees. There's no data races, which is great, but doesn't really impact our usage because we have a single-threaded execution cycle. But the one that really is useful to us is no garbage collection. So the combination of memory safety and no garbage collection means that we have really good performance guarantees without needing the overhead of that garbage collector. So what's our code base look like? Our library is a load time function randomization, which takes a set of functions and randomizes it as a security measure. And it's all in one big shared library. It's about 30,000 lines of C++. It's got limited templating, no polymorphism, so hopefully a good candidate to move over to the Rust side. We have to use syscalls directly. We don't want any dependencies on libc. We have a bunch of different algorithms for shuffling, safety, layout, a lot of stuff there. And we also have to do rewriting of relocations in the ELF file. A handful of parsers, each of which their own little quirks and quibbles, which has always drawn some concern for the correctness of those parsers. And we also have to support multiple target architectures with inline assembly. So what are our goals here? We'd like to take our C++ and turn it into Rust. Ideally, we should get a performance on par with C++. We really want binary sizes roughly the same size. We really just don't want any degradation anywhere. That's the baseline. Our new implementation should pass all of our existing tests, and it should exhibit any external behaviors that were measurable before. And in the process of the rewrite, we would really like to convert it into idiomatic Rust. So it should look like someone started the project in Rust and used types like option for nullability, result for error handling. It should look clean, or idiomatic is usually the term used. We'd also like to use functional style iteration as opposed to imperative loops when there's a good argument for it. We'd also like to avoid any large unnecessary refactors, so the source conversion can be easily compared to the original input. So you have a C++ and a Rust side by side. You should be able to see the clear correlation between those two pieces of code. That's the goal. We didn't quite hit that in a few circumstances, but I'll mention that later. We'd also like to limit or isolate the use of unsafe Rust. So if we convert all of our code to Rust and it's mostly unsafe, we really didn't benefit from that conversion. So in that vein, we really want to avoid FFI, CFFI as much as possible because there's a lot of unsafety introduced there, and we'd also like to avoid any external non-Rust dependencies. And since we're building it all into one shared library, that's a reasonably achievable goal if we're converting almost everything into Rust. But what are our complications? So our library has a few gotchas in it because of the security context that it's running in. So we're not able to use the Rust standard library because we don't want that dependency on libc. So we're going to be running no standard build, and we're going to be using direct syscalls only for any host interaction. We don't want any dynamic library dependencies as well, any dependency that we have would be something we wouldn't be able to protect with our randomization software. So what does our existing C++ cause us some problems with? Well, templating does not always map cleanly onto Rust generics. So in certain circumstances, we had to find interesting approaches to porting some of our templated code. And the bigger problem was that C++ has an assumption of pretty much if you want to mutate something, you're welcome to try, buyer beware. So in our existing code base, we had a lot of places where we'd read our internal metadata and immediately access an arbitrary pointer from that metadata and just start writing. And Rust really doesn't like that because it expects you to have clear ownership rules. You shouldn't be accessing global mutable state because then you might be invalidating some of the rules around its safety requirements. And the other kind of pain point was that we can't use Rust on certain esoteric targets. If you've got a somewhat unsupported little microcontroller, micro device, whatever, that Rust doesn't target, that could be a problem. So we don't want to leave behind too many platforms, but sacrifices must be made sometimes in progress. So what does our conversion end up looking like? Well, we have to take a step back. If you're going to convert any code, you better have good test coverage. You probably will need to improve it because you'll find edge cases along the way that you hadn't quite considered or behavior that was a little undefined along the way. You also need to decide between whether you want to do a manual or, quote, automatic conversion. So we ended up going the manual route, but there are some automatic tools that allow you to convert C specifically over into Rust. There's C2 Rust. That doesn't produce a super idiomatic looking Rust. It's preserving completely the semantics. And there's also some experimental tools out there that are trying to apply AI or LLMs to converting between languages, notably the DARPA Tractor program. So from there, if you have well-defined interfaces, you may be able to slice and dice your code base and do partial conversion. That's a great idea because it gives you better testability. The downside is that FFI is usually pretty error prone when you're interacting with functions. You have to make sure you uphold the guarantees of pointers crossing that boundary. Anything that goes through there, it's very possible that you will introduce a failure mode in that FFI, even using generated bindings to C or C++. I would recommend using the CXX crate for auto-generated FFI if you're trying to maintain a mixed code base. Unfortunately, we weren't able to leverage that at the time because it did not support our complications mentioned earlier about the no standard library support. These days, it sounds like it should support it, but we've already converted that all into Rust. If you are planning a full conversion, make sure that you do try to define boundaries of where you can rewrite individual parts and make sure the boundaries are very clear just so you can get that ball rolling. It can take a while to look at a big ball of C++ and decide where you can actually start kind of trimming off and converting into Rust. I would recommend starting with all your higher level C++ interfaces, class structure functions, and just trying to build a skeleton, kind of the full call tree of your application so that you can see how your ownership of data is being passed around through your code base. That will help you identify places where you either didn't expect to have mutability or you needed mutability. And in particular with Rust traits and generics, you really want to make sure that you can build out kind of the whole skeleton of your code base. So leaving a lot of function bodies unimplemented is very useful for that practice. You want to identify that early so that any refactors can be known in advance, because while Rust is good at refactoring, if your whole project needed to be refactored because of something in C++ that was very ambiguous with its ownership, that could be a real problem. But then after that, you just proceed with a largely mechanical conversion. A lot of C++ ends up looking a lot like a lot of Rust. So just converting the function bodies, capturing those semantics, that can be pretty good for a first approximation. Then doing a secondary pass where you end up converting more and more types over to the Rust native types. Like I said earlier, option, result. maybe even introducing some new types in there so that you can more easily handle things that were maybe a little ambiguous, like just integers that happen to be passed around between multiple functions might have better semantic properties you can apply to them. But again, we're back to that problem area. We've got some global mutable state that we need to deal with. But before we get onto that, I'm going to mention you should really use Clippy as like a pair partner programming in your new Rust codebase, because it will provide you a lot of tips and tricks along the way to clean up the code as you're making it. In this case, it's recommending that you, instead of taking a reference to a dynamic vector, that you instead pass a Rust slice, which is a much more general type that many other types can be coerced to cleanly, and that will keep your code base a lot cleaner and produce code that more people can leverage, more developers can leverage. So back to our global mutable state problem. So we need to interact with a bunch of raw memory addresses all over the place, and we really want to control that interface. So we end up building this nice memory access trait, which has like read and write pointer addresses. And what we end up doing is when we initialize our Rust base with some unsafe code, we collect the slices of memory that would have normally been a global reference that could have been accessed by anyone, and now control that access through this trait, which can be queried so that you can interact with all of those arbitrary addresses and get a lot of benefits like bounds checking. We end up limiting that unsafe code to the initialization. That's great. There's no unsafe code in that interface, and anybody else can implement that interface for any arbitrary backend that we might want to use. And that's where we saw a great benefit of the trait system, is that because we've now cordoned off all of those memory accesses, we're able to use this trait in our live process, as well as implementing additional optimizations on ELF files directly on disk, or even being able to store the memory itself in dynamic vectors and not have to touch the process itself, and allow us to keep that around for other purposes. So what does that look like in this case? Well, it turns what was in C++ a direct memory access to an arbitrary pointer, rewriting that 32-bit integer, into a call through the memory trait, which allows us to write a given virtual address at that address. And the important part here is that if you screwed up in C++, you might have just written somewhere that you didn't anticipate. In Rust, now we are returning a result type from that value. We get bounds checking on those slices that we had before, and we could either handle an error here that maybe somebody tried to write out of bounds, we could panic, we could handle it, but most importantly, we would have an error that we are aware of. In C++, you would only know if there was an error in that if you had written out of a legal memory segment, which wouldn't be great either, but you could have written potentially just arbitrary memory locations. So one of the benefits we also saw was that we were able to use Rust custom allocators in our no standard environment. So because of that, every line of code that we write outside of some of that unsafe stuff ends up looking just like normal Rust code. So even though we're in that really specialized environment with no standard library, we're still able to use a portion of the standard library called core, which means that we can leverage all the vector types, hash maps, whatever we want, and we don't have to vendor it into our Rust code, which we were doing in C++ because we had to handle special memory access, or memory allocation rather. Another benefit that we saw was that we were immediately able to use existing external Rust crates. Even though we've got all these complications about how we need our library to function, many of these crates out there do support no standard library support, which means that we can just interact with them. We have our own memory allocator, they can use our memory allocator. We were able to very quickly import an entire TOML parsing library, no memory allocation concerns, no memory safety concerns, living within our ecosystem, and it definitely improved the velocity of what we were able to do in our library. We also found that we were able to compile things a lot easier. I'm sure everybody has great stories about CMake, and we found that we were able to convert most of our CMake over to Cargo, and it was a lot simpler to work with. So now that you've got this big ball of Rust code, how do you know it actually does what you want? Well, that's where the testing comes in. We really want to verify the correctness with our existing test infrastructure. That's a great thumbs up. We'd also like to implement comparative testing. We want to make sure that whatever the original binary did, the new one should too. So we'll talk about that in a moment. And we also want to leverage Rust unit testing to further guarantee a lot of the kind of the internal mechanisms of our code. And I'm going to recommend using PropTest here, which is a Rust testing library that allows you to verify properties of Rust code. In this case, it takes two arbitrary integers, and if they add together and match the output of add, everything's great. If it fails, it will actually help try to minimize the example that causes the failure. If you want to see a great example of this usage, you should check out Colin Breck's talk from earlier this week on Rust and C++. So from our comparative testing, what we really want to do is run both implementations, ideally in the same process, which we can do because we have the existing C++ and we can merge in our Rust. And we run both either in parallel or sequentially. We have that flexibility now. And with that, we're able to compare our memory regions byte for byte. So even if there wasn't a visible behavior in a test case failing, we can now know that there are places in our code base where they diverged, because the final randomization of the process's memory is very specific, and any deviation would mean that there's a bug in one or more of the implementations. And once we found those bugs, we can add additional tests to catch any of those bugs in the future. The benefit of what I mentioned earlier, that memory access trait, is now we're able to intercept those memory modifications, store them in dynamic vectors. The Rust implementation doesn't even have to write it out into the memory segment itself for us to compare both implementations. So what did we get out of all this? Well, it took about 3 months of conversion time for one engineer to convert 30,000 lines of code, and a few extra months to iron out some problems on a platform that we did not have direct access to, and the turnaround time on it was not great for any additional code changes. We found a lot of bugs. We found a lot of incorrect argument types in some of our syscall wrappers. We found a lot of C++ switch statements that weren't necessarily setting all the values expected in each switch statement. Some of our internal parsers had issues where they might overrun their buffer and read in an innocuous fashion, but it was still reading past the end of the buffer in a couple of cases. There was also the possibility of some out-of-bounds memory reads that wouldn't have been necessarily detected in the C++ code. Again, they weren't actually being used in that fashion. And then we also had a lot of conversion problems around C++'s implicit integer coercion. There was a lot of code where you'd have auto this equals some computation, auto that equals some computation, and it wasn't always clear how C++ was either truncating or extending some of the integers, and that was causing some loss in precision. So our initial metrics look pretty good. There's about 30,000 lines of C++ code, 30,000 lines of Rust. Sure, we got rid of all those header files, but we had to add some additional scaffolding, as mentioned in things like the memory access trait, to make all of this kind of hang together. Additionally, like our standard library wrappers gave us a lot more idiomatic Rust instead of having direct C function calls. We ended up with about 30 functions of unsafe Rust, which amounted to about 500 lines of code, excluding the automated bind gen output for the automated bindings. So that gives us roughly like 1.5% of our code base is in unsafe, which is a pretty good number. Our file sizes went down. That was unexpected. We were really kind of anticipating larger growth. And our runtime was 2x slower. Wait a second, 2x slower, that's not acceptable. That doesn't meet our goals. So initially, we thought it was going to be mostly C++ was doing a lot of random accesses that weren't being bounds checked, and that was introducing a lot of overhead. But profiling ended up leading us to a lot of targets that we would have otherwise not seen. And there was cases where refactoring here allowed us to iterate over some of our internal metadata just once instead of twice, which would have been a difficult refactor in the original C++ code base. There's a handful of other things that we fixed here, but that's the one I really wanted to highlight. But as you can see, as we fixed a handful of things, which amusingly didn't actually take all that long to identify and fix, brought us gradually back down to about 1x. So there we are, 1x. This is a pretty successful outcome for all of our metrics we wanted. And then back to safety. So like I said earlier, we had about 1.5% of our unsafe code is out there, and that means the rest, 98-ish%, is all in safe code. So all of our reviewing effort can really be focused on some of those unsafe code segments and verifying that their correctness, rather than that other 98%, which we know because of Rust guarantees are not going to introduce any memory unsafety. So the things here listed are the unsafe code, and they're all behind safe abstractions now. You don't, as a user of some of these crates, you don't end up having to use unsafe code at all. And we avoided using unsafe for any performance considerations in some of that performance work that we just talked about. So again, what's our safe code? Everything else. Randomization, memory layout, relocations, internal parsers, it's great. We have a lot more confidence in a lot of our code out there. But there were some problems. We do know that there are certification concerns around Rust. We've been having some trouble finding companies that are interested in certifying Rust for various standards. We are relying on a handful of unstable features for our no standard work. It would be great if Rust supported better symbol visibility annotations. It doesn't currently do that. And then there's a list of items that are very specialized for interacting with some of the low-level work that we're doing. But those could change someday or even be removed entirely, and that's a little bit of risk on top of what we're doing on the Rust side. Additionally, there's a bus factor. There's fewer people in our company and externally that are familiar with Rust over C++. And again, back to the very beginning, we know that Rust doesn't support as many targets as GCC, which could potentially limit our ability to port this to some complicated platforms. Some of the good surprises along the way, we found that we were able to have really heavy code reuse. It's a lot easier to modularize your Rust than it was C++ and still maintain the guarantees you wanted. The composability was really good. So we were able to leverage our existing code in Rust and easily port it into different Python plugins via PyO3. We were able to use in a lot of external utilities the exact same code base that was in our really kind of complicated special case library, but because of the abstractions in place, we're able to use them in a more traditional Rust application that doesn't require special nightly features. We were also able to have really confident refactoring during this process. Once we had a working implementation, it was very easy to identify locations and restructure code as necessary. Unlike C++, where, especially in our special case library, that there were cases where it wasn't always clear that even moving code around would maintain the same correctness levels. So, final thoughts from all this. We thought it was a success. We have about the same amount of code. It's a lot easier to work with now because of all the constraints that the compiler imposes on us. We have less CMake, more cargo. That's always a win. And we met all of our goals that we set out to, even though we had to work a little bit on the performance end. What would we have done differently? We would have definitely added more tests. Like, you can never have enough tests. And we would have had better automation of testing on some of those platforms that ended up causing us a lot of time of back and forth. There's definitely a bottleneck there in the conversion. And even though we have a relatively small code base, we would have still benefited from splitting it up into smaller chunks, even if we had to spend more time with FFI scaffolding during that conversion process. It would have been much easier to identify parts of that code base in isolation rather than having a full conversion that we depended more on our test suite to verify. So should you, quote, rewrite it in Rust? Well, that kind of depends on how important memory safety is to you and how often you're chasing bugs that depend on kind of sketchy behavior or perhaps not as well-defined behavior in C++. And ultimately, how much code do you really need to rewrite? I don't expect anybody to be writing, their billion line code base. That's just not feasible from cost or time effectiveness. But you might be able to find a small portion of that code base that you know to be potentially fraught or problematic in terms of memory safety concerns, or even just that fragile code that nobody really wants to touch because it's not entirely clear what side effects it may have. So take all that into consideration and maybe consider either converting stuff into Rust or considering it for your next greenfield project. Thank you. So I can take questions in the middle here if anyone has any.
That was a great story. Thank you. What'd you use for profiling? Is that flame graph work? Or?
We ended up using mostly Valgrind's call grind functionality. That worked really well for giving us repeatable numbers. Because of the amount of like syscall stuff, we were getting really odd numbers by keeping tabs of like wall clock time. So getting just raw instruction counts was the easiest way to pare that down.
Thank you.
All right, no further questions. Thank you all for your time.